Tonight, as you settle into stillness, consider that the universe you inhabit is stranger than common sense suggests. The space around you and the time flowing through your experience are not separate, independent things. They are woven together into a single fabric, space-time, that can stretch, compress, warp, and curve. This is Einstein's revolutionary insight, perhaps the most profound reimagining of reality in human history. As your breath slows and deepens, think about how you normally conceive of space and time. Space seems like an empty stage where events occur. 3 dimensions of length, width, and height, forming a container for matter and energy. Time seems like a separate river flowing steadily forward, carrying you from past through present into future. They appear completely distinct. Space is where things are. Time is when things happen. But Einstein discovered something remarkable. Space and time are not separate. They form a unified 4-dimensional continuum called spacetime. Every event in the universe has 4 coordinates, 3 spatial dimensions plus 1 time dimension, and these 4 dimensions are fundamentally interconnected. What one observer experiences as space, another observer moving at different velocity experiences, partly as time. Space and time mix together, blend into each other, transform from one to the other depending on motion and gravity. This isn't merely philosophical speculation or mathematical abstraction. This is the confirmed structure of physical reality, tested and verified through countless experiments. The GPS satellites orbiting above you right now must account for relativity, or your navigation would accumulate miles of error every day. Time literally runs at different rates, at different heights in Earth's gravitational field, and at different velocities. The phone beside you contains technology that only works because engineers account for spacetime's strange properties. Tonight, let us explore this beautiful, counterintuitive theory. Let us discover how motion through space affects the passage of time, how gravity warps the fabric of space-time itself, how light always travels the same speed regardless of reference frame, and how these strange facts combine to reveal that reality operates by rules profoundly different from everyday intuition. As sleep approaches, let your mind drift through the curved geometry of space-time, discovering that the universe is more elegant and more strange than it appears. You have already experienced relativity today, though you didn't notice. Light from the sun took 8 minutes to reach Earth, but from the photon's perspective, traveling at light speed, the journey was instantaneous. Time dilation at extreme velocities means that light experiences no passage of time. The photon that struck your eye this morning was born at the sun's surface and died in your retina with no subjective duration between. 8 minutes for you, 0 time for the photon. Right now, as you lie still, you are moving through space-time at the speed of light. Not through space, you're relatively motionless, but through space-time. Everything in the universe moves through the 4 dimensions of space-time at exactly light speed. When you're stationary in space, all your motion is through time. When you move through space, some of your motion through space-time redirects from the time dimension into spatial dimensions, which is why time slows down for moving objects. You have only so much motion to distribute across 4 dimensions, and velocity through space uses up some of the motion that would otherwise carry you through time. As you rest, imagine space-time not as emptiness, but as something real, a flexible fabric that can be stretched, compressed, twisted, and curved by the presence of mass and energy. Earth sits in space-time like a bowling ball on a trampoline, creating a depression, a curvature in the fabric. This curvature is what you experience as gravity. You're not being pulled toward Earth's center by a mysterious force acting at a distance. You're following the straightest possible path through curved spacetime, and that curved geometry guides you toward Earth's surface. This is the profound beauty of general relativity. Gravity is not a force, but geometry. Mass tells spacetime how to curve. Curved spacetime tells mass how to move. The planets orbit the Sun, not because the Sun pulls them with invisible strings, but because the Sun's mass curves spacetime, and planets follow the curves, like marbles rolling along the depression in a stretched rubber sheet. Tonight's journey will take us from special relativity, which united space and time and revealed the strange effects of velocity, to general relativity, which showed that gravity is the curvature of space-time itself. We will explore time dilation and length contraction, the relativity of simultaneity, light speed as the universe's speed limit, gravitational time dilation, frame dragging, gravitational waves, and the prediction that space-time can be so severely warped that not even light escapes. Black holes, where space-time curves back on itself and time itself appears to stop. These are not thought experiments or science fiction, but verified features of the universe you inhabit. You live in curved space-time. Time passes at different rates for you, depending on how you move and where you stand in gravitational fields. The solid distinction between past, present, and future that seems so obvious is actually frame-dependent, and events that are simultaneous for you occur at different times for someone moving relative to you. As sleep approaches, let yourself feel wonder at inhabiting a universe where space and time interweave, where geometry determines motion, where traveling fast enough lets you journey into Earth's future while barely aging yourself, where massive objects warp the very fabric of reality around them. Einstein's universe is strange and counterintuitive, yet it is our universe, the one we measure, the one we inhabit, the one whose strange properties make possible GPS, particle accelerators, accurate astronomy, and perhaps, someday, if we're fortunate, travel to distant stars. Rest now in this understanding. You are not in space-time like an object in a container. You are part of space-time, moving through it at light speed, following geodesics through its curved geometry, experiencing its flexibility as gravity, its structure as the flow of time. Tonight we discover that reality's foundation is more beautiful and strange than common sense ever imagined. Special relativity, when motion warps space and time. As your muscles relax and your mind drifts into receptive calm, let us begin where Einstein began, with a simple question that had profound consequences. The year was 1905, and Einstein asked, "What if the speed of light is the same for all observers, regardless of how they're moving?" This seemingly innocent assumption shattered classical physics and rebuilt our understanding of space and time from the ground up. Consider light traveling from a distant star toward your eye. Classical physics said light should work like anything else moving through space. If you move toward the source, you should measure the light traveling faster. If you move away, you should measure it traveling slower. Just like a ball thrown from a moving car travels faster relative to the ground than a ball thrown from a stationary position. But experiments revealed something strange. light always travels at exactly the same speed, 299,792,458 meters per second, regardless of the observer's motion. Measure light's speed while standing still, 299,792,458 meters per second. Measure it while moving toward the source at half light speed, still 299,792,458 meters per second. This makes no sense according to classical addition of velocities. It violated everything physicists thought they understood about motion. Einstein realized that if light speed is constant for all observers, something else must be flexible. Space and time themselves must adjust to keep light speed invariant. If you move quickly relative to me, your measurements of space and time must differ from mine in precisely the way needed to ensure we both measure light traveling at the same speed. This was the revolutionary insight of special relativity. Picture, as you rest, two observers. Alice stationary on Earth, Bob travelling in a spaceship at 87% of light speed. Alice shines a light beam forward. She measures its speed, exactly light speed. Bob, travelling nearly as fast as light itself, might expect the light to barely outpace him. But when he measures its speed, he also gets exactly light speed. How is this possible? The answer is time dilation and length contraction. From Alice's perspective, time passes more slowly for Bob. His clocks run slow, his heartbeat slows, his aging slows. From Bob's perspective, distances in his direction of travel are contracted. The distance to his destination is shorter for him than for Alice. These adjustments, slower time and contracted space, occur in exactly the proportions needed to ensure both observers measure light at the same speed. As sleep draws nearer, consider what this means. Time is not absolute. There is no universal clock ticking at the same rate everywhere in the universe. Your experience of time's passage depends on your velocity relative to other objects. Move fast enough and you age more slowly than someone stationary. Travel in a spaceship at 99.9% of light speed for what feels like 1 year to you, return to Earth, and you'll find that decades have passed for everyone else. You will have traveled into Earth's future. This isn't science fiction, it's verified physics. Particles accelerated to near light speed in particle colliders live much longer than identical particles at rest, exactly as relativity predicts. Atomic clocks flown on airplanes tick slightly slower than identical clocks on the ground. GPS satellites experience time dilation both from their velocity and from being higher in Earth's gravitational field, and GPS calculations must account for these effects, or navigation would fail. Length contraction is equally real. An object moving relative to you appears compressed in its direction of motion. A spaceship travelling at 87% of light speed appears to you only half as long as it does to passengers inside it. This isn't optical illusion. Space itself is contracted from your reference frame. The meter stick inside the spaceship is genuinely shorter when measured from your frame of reference, even though it appears normal length to someone travelling with it. Then there's the relativity of simultaneity, perhaps the strangest consequence of special relativity. Events that occur at the same time for one observer occur at different times for an observer in relative motion. Simultaneity is not absolute, but frame-dependent. If two distant events appear simultaneous to you, someone moving rapidly relative to you will observe one event happening before the other. Imagine, as you drift towards sleep, Alice and Bob again. Alice sees two supernovas explode simultaneously in opposite directions across the galaxy. But Bob, traveling at high speed, sees one supernova explode before the other. They disagree about what "at the same time" means. Neither is wrong. Simultaneity genuinely depends on reference frame. There is no absolute present moment extending across the universe. The very concept of now is observer-dependent. This has philosophical implications that troubled even Einstein. If simultaneity is relative, the distinction between past, present, and future becomes blurred. Events in your future, according to your reference frame, might be in someone else's past, according to their reference frame. In some sense, all of space-time, past, present, and future, exists equally, just as all locations in space exist equally. You experience time as flowing, because your consciousness moves through space-time along your world line, but the entire four-dimensional structure exists timelessly. Special relativity also reveals why nothing with mass can reach light speed. As objects accelerate, they gain not just kinetic energy, but relativistic mass. The closer you get to light speed, the more energy is required for further acceleration. Reaching light speed would require infinite energy, which is impossible. Light speed is the universe's ultimate speed limit, not because of any arbitrary rule, but because of space-time's structure itself. Only massless particles like photons can travel at light speed, and they must always travel at that speed. They cannot slow down or speed up. From a photon's perspective, if it could have a perspective, space-time is completely contracted in its direction of travel, and time doesn't pass at all. The photon's entire existence, from emission to absorption, occurs in a single instant with zero spatial separation, even if, from your perspective, it traveled for billions of years across the observable universe. As you rest, consider mass-energy equivalence. Einstein's famous E equals mc squared. Mass and energy are not separate entities, but are different forms of the same thing. Mass is concentrated energy. Energy has mass. A hot object weighs more than an identical cold object because thermal energy has mass. When matter and antimatter annihilate, their mass converts completely to energy. When energy concentrates sufficiently, it can produce particle-antiparticle pairs, converting pure energy into matter. This equation explains why stars shine. The Sun converts 4 million tons of mass into energy every second through nuclear fusion, and that energy, released as light and heat, is literally the converted mass of hydrogen atoms. The sunlight touching your face this morning was matter yesterday, transformed into energy by the equivalence Einstein discovered. Special relativity unified space and time, mass and energy, revealed that simultaneity is relative, that time dilation and length contraction are real, that light speed is the universe's speed limit, that traveling fast enough lets you journey into the future. These aren't philosophical speculations, but measured features of reality, confirmed by every experiment designed to test them. Tonight, as sleep approaches, know that you live in a relativistic universe where space and time interweave, where velocity determines the passage of time, where moving fast slows your aging, where simultaneity depends on reference frame, where light speed is constant and absolute, and utterly fundamental to space-time structure. The universe revealed by special relativity is strange and counterintuitive, yet it is precisely the universe we inhabit, elegant, mathematical, and far more interesting than the absolute space and absolute time that Newton imagined. Gravity curves, space-time, general relativity's beautiful insight. As your breathing settles into the rhythm of approaching sleep, we arrive at Einstein's greatest achievement. General relativity, the theory that revealed gravity, is not a force, but the curvature of space-time itself. Where special relativity unified space and time, general relativity showed that this unified space-time is flexible, dynamic, and curved by the presence of mass and energy. Picture, as you rest, a two-dimensional analogy that helps visualize four-dimensional reality. Imagine space-time as a stretched rubber sheet. Place a bowling ball on the sheet and it creates a depression, warping the previously flat surface. Now roll a marble near the bowling ball. The marble follows the curved surface, spiraling around the depression. It's not being pulled by the bowling ball through some mysterious force. It's simply following the straightest possible path through the curved geometry. This is how gravity works in our universe. The Sun creates a depression in space-time. Earth follows the curved space-time around this depression, and we call that orbital motion. You stand on Earth's surface because Earth curves space-time, and you follow that curvature. Gravity is not a force pulling you down, but the shape of space-time telling you how to move. You are following a geodesic, the equivalent of a straight line in curved space-time. Einstein's field equations describe precisely how mass and energy curve space-time, and how curved space-time determines the motion of mass and energy. These equations are simple in concept, though complex in detail. Mass-energy tells space-time how to curve. Curved space-time tells mass-energy how to move. It's a beautiful feedback loop. Matter shapes geometry. Geometry guides matter. As sleep draws nearer, consider the predictions that emerged from general relativity, each one initially shocking, all of them confirmed by observation. Light bends around massive objects because light follows space-time's curvature. During a solar eclipse in 1919, astronomers observed stars whose light passed near the Sun, appearing displaced from their true positions, exactly as Einstein predicted. The Sun's mass curved space-time, and light followed those curves, appearing to bend from our perspective. Gravitational time dilation is even stranger than velocity time dilation. Time passes more slowly in stronger gravitational fields, or equivalently deeper in space-time's curvature. A clock on Earth's surface ticks slower than an identical clock on a mountaintop. A clock near a black hole ticks far slower than one far away. This isn't due to the clock's malfunctioning. Time itself passes at different rates at different positions in a gravitational field. GPS satellites experience this effect. They orbit about 20,000 kilometers above Earth's surface, where gravity is weaker, so time passes faster for them than for clocks on the ground. Without correcting for this gravitational time dilation, GPS positioning would accumulate errors of several kilometers per day. Your phone calculates your location correctly only because its software accounts for curved space-time's effect on time's passage. Imagine resting on a neutron star's surface, where gravity is billions of times stronger than Earth's. If you could survive the conditions, your time would pass normally from your perspective. But if Earth observers could somehow watch you, they would see you moving in extreme slow motion, each of your seconds lasting many Earth seconds. You would see Earth's time racing forward. This is real time dilation caused by space-time curvature, as real as the ground beneath you, as fundamental as any feature of the universe. Consider black holes, regions where space-time curves so severely that nothing, not even light, can escape. Form when massive stars collapse, compressing their mass into infinitesimal volumes, creating such extreme space-time curvature that a boundary forms, the event horizon, beyond which escape is impossible. Anything crossing this boundary is pulled inexorably toward the singularity at the center, where space-time curvature becomes infinite and our physics breaks down. Near a black hole's event horizon, time dilation becomes extreme. Watch someone fall toward a black hole and you'll never see them cross the horizon. From your distant perspective, they appear to slow down asymptotically, freezing at the event horizon, their image redshifting and fading as time dilation becomes infinite. But from the falling person's perspective, they cross the horizon in finite time, experiencing nothing special at that boundary, continuing toward the singularity where tidal forces eventually tear them apart. Black holes are not theoretical speculation, but observed reality. We've detected them through their gravitational effects on nearby stars, through the X-rays emitted by matter heating as it spirals into them, and recently through direct imaging of the glowing accretion disk around the supermassive black hole at our galaxy's center. They exist. They are precisely where general relativity says they should form, and they behave exactly as the equations predict. As you drift towards sleep, consider gravitational waves, ripples in space-time itself, traveling at light speed, predicted by Einstein in 1916, directly detected by LIGO in 2015. When massive objects like black holes or neutron stars orbit each other and merge, they shake space-time violently enough to send waves propagating across the universe. These waves stretch and compress space itself as they pass, and LIGO detected them by measuring space distortions smaller than 1/10,000th the diameter of a proton. Gravitational waves prove that space-time is not merely mathematical abstraction, but physical reality, something that can vibrate, carry energy, propagate like waves on water's surface. Every massive object accelerating creates gravitational waves, though usually far too weak to detect. The mergers of black holes and neutron stars create waves strong enough to measure after traveling billions of light years, allowing us to observe the universe through an entirely new sense, feeling space-time's vibrations rather than seeing electromagnetic radiation. Frame dragging is another prediction. Rotating massive objects drag space-time around with them, like honey stirred by a spoon. Earth's rotation drags space-time, creating tiny effects on satellite orbits that have been measured and confirmed. Near a rotating black hole, the frame dragging becomes so severe that space itself rotates, making it impossible to remain stationary. You're forced to orbit in the direction of the black hole's rotation, even if you're hovering above the event horizon with powerful rockets. Picture yourself as sleep approaches, not as existing in some absolute unchanging space, with time flowing uniformly forward, but as embedded in dynamic, flexible space-time that curves around every massive object, where time's passage varies with position and velocity, where the geometry of reality itself is shaped by matter and energy, where the distinction between space and time blurs into unified four-dimensional continuum. General relativity reveals that gravity is geometry. The falling apple is following geodesics through curved spacetime. Planets orbit stars because stars warp spacetime, and planets follow those warps. You stand on Earth's surface because you're trying to follow your geodesic through spacetime, but Earth's surface prevents you, creating the sensation you interpret as weight. Gravity is not a force acting across space, but the shape of spacetime telling you how to move. This theory predicts the universe's large-scale structure and evolution, that space itself expands, carrying galaxies apart, that the universe had a beginning in the Big Bang, that massive objects can collapse into black holes, that gravitational waves exist, that GPS requires relativistic corrections. Every prediction tested has been confirmed. General relativity is not merely correct, but precisely, quantitatively, exquisitely accurate across all scales, from laboratory experiments to cosmological observations. Tonight, as you rest, you are embedded in curved spacetime, following geodesics, experiencing gravity as geometry, aging at a rate determined by your position in Earth's gravitational field and your velocity through space. The fabric of reality flexes around you, curves beneath you, determines how you move through the four dimensions of spacetime. This is not poetry, but physics. The confirmed structure of the universe you inhabit, revealed by Einstein's profound insight that gravity is not force, but curvature, not action at a distance, but the shape of reality itself. Time's strange nature, past, present, future, reconsidered. As your body settles into deepening rest, let us contemplate what relativity reveals about time itself, that strange dimension that seems so different from space, yet is fundamentally woven together with it. The flowing present moment you experience, the distinction between past and future, even the arrow of time pointing from earlier to later, all of these familiar features become mysterious in light of relativity's insights. In everyday experience, time seems to flow. The present moment feels special, real in a way that past and future are not. The past is fixed, over, unchangeable. The future is undetermined, open, full of possibilities. And the present is that knife edge between them, the only moment that truly exists, constantly moving forward, transforming future into present, into past, as time flows inexorably onward. But relativity reveals that this flow is not built into spacetime's structure. The four-dimensional geometry of spacetime simply exists, all events at all times existing equally in what physicists call the block universe. Your birth, this moment of reading, your future death, all of these events exist at different locations in spacetime, just as different cities exist at different locations in space. You experience time as flowing because your consciousness moves through spacetime along your world line, encountering events sequentially. But the events themselves don't flow, they simply are. Picture, as sleep draws nearer, spacetime as a loaf of bread. Each slice represents space at a particular time. All the slices exist simultaneously in the four-dimensional loaf. You experience one slice at a time as your consciousness moves through the loaf, but the whole loaf exists timelessly. Past slices don't disappear. Future slices aren't unreal. they're all equally present in the four-dimensional structure. This view, called eternalism or the block universe, troubles many people. If the future already exists in spacetime, how can we have free will? How can our choices matter if everything is already determined? But notice that this confuses already exists in spacetime with already determined. The block universe says all events exist at their respective locations in time, not that future events are determined by past events in some clockwork fashion. Your choices still shape what happens. They're part of the causal structure determining which world line through spacetime you follow. Consider the relativity of simultaneity again. The fact that observers in relative motion disagree about which events occur at the same time. If simultaneity is observer-dependent, the very notion of the present moment becomes problematic. There is no absolute present extending across the universe, no universal now. Events simultaneous for you occur at different times for someone moving relative to you. Your present moment is not everyone's present moment. This implies that the distinction between past, present, and future is perspective dependent, like the distinction between left and right. Just as left and right depend on which way you're facing, past, present, and future depend on your motion through spacetime. Events in your future, according to your reference frame, might be in the past, according to someone else's reference frame. The flowing present moment is an illusion created by consciousness moving through spacetime, not a fundamental feature of reality. As you rest, consider what physicists call the arrow of time, the apparent asymmetry between past and future. Causes precede effects. Eggs break but don't spontaneously reassemble. Entropy increases. You remember the past but not the future. Why does time have an arrow when physics equations work equally well running forward or backward? The answer likely involves entropy, the second law of thermodynamics, stating that disorder tends to increase in closed systems. The early universe was in an extraordinarily low entropy state, highly ordered, and entropy has been increasing ever since. The arrow of time, our perception that time flows from past to future, might be nothing more than entropy increasing, disorder spreading, possible states proliferating. We remember the lower entropy past, but not the higher entropy future, because memory formation itself is an entropy increasing process. Yet, at the fundamental level, physics equations are time symmetric. If you recorded particles' positions and velocities at one moment, then reversed all velocities and let the system evolve, it would retrace its history backward. The laws of physics don't prefer one time direction over another. The arrow emerges from initial conditions and statistical mechanics, not from time itself having an inherent direction. This raises profound questions about the nature of time. Is time fundamentally different from space, or is the difference merely in how we perceive it? Why does consciousness seem to move through time but not through space? Why can we remember past but not future if both exist equally in space-time? These questions remain at the frontier of physics and philosophy, unresolved despite relativity's insights. Some physicists suggest that time might not be fundamental at all. Perhaps at the deepest level of reality, in quantum gravity, theories that attempt to unify relativity and quantum mechanics, time emerges from something more basic, just as temperature emerges from molecular motion. Perhaps the universe at its foundation is timeless, and time appears only at larger scales as an emergent property of quantum interactions. As sleep approaches, contemplate closed time-like curves, solutions to Einstein's equations that loop back on themselves, theoretically allowing travel into your own past. These solutions exist mathematically, but probably not physically, as they create causality paradoxes. Still, their existence in the equations reveals that time is stranger than common sense suggests, that the prohibition against time travel is not obviously fundamental, that the equations describing spacetime allow possibilities that seem impossible. Consider also time dilation's implications for time's nature. Time literally passes at different rates in different reference frames. There is no absolute cosmic clock ticking uniformly throughout the universe. Every clock measures its own proper time along its own world line through space-time. Your aging is the length of your world line through four-dimensional space-time, and different paths between the same two events can have different lengths. This means time is not a universal background against which events occur, but is itself relative, flexible, intertwined with space. The seemingly obvious distinction between space and time, that you can move through space but not through time, that space has 3 dimensions but time only 1, becomes less clear. You do move through time at 1 second per second along your world line. Time does have dimension, just like space. The main difference is that time-like world lines are restricted. You can only move forward through time, not backward, while space-like directions are symmetric. Picture yourself as you drift toward unconsciousness, not as existing at a single moment in time, but as a 4-dimensional structure extending from birth to death through space-time. Your entire life, every moment you've experienced and will experience, exists as a connected world line through the block universe. You are not a 3-dimensional object moving through time, but a 4-dimensional object, a space-time worm extended in time just as you're extended in space. This perspective suggests that past and future are as real as present, that the flowing present is perspectival rather than fundamental, that all moments of your life exist equally at their respective locations in time, that the universe is not changing but simply is, a timeless 4-dimensional structure within which consciousness moves along world lines, creating the illusion of flowing time. Yet this view doesn't diminish experience or make moments less meaningful. Each moment still occurs, still is what it is, still contains the joy or sorrow or wonder you experience there. That all moments exist eternally in the block universe doesn't make present experience less real. It makes all experience equally, eternally real. As you fall asleep, time will seem to pass, hours elapsing between when you close your eyes and when you wake. But in space-time's 4-dimensional geometry, your sleeping and waking both exist, separated not by time passing, but by spatial separation along the time dimension of your world line. Sleep and wake are different locations in space-time, and you traverse between them, not because time flows, but because your consciousness moves along the world line connecting them. Time remains mysterious even after relativity's revelations. We understand its geometry, its flexibility, its interweaving with space, but why we experience it as flowing, why consciousness moves through it in one direction, why the present moment feels special despite simultaneity being relative, these questions remain profound and puzzling. Time is not what it seems. Yet what it is remains, in some ways, as mysterious as ever. The cosmos in relativity. From Big Bang to black holes. As your muscles fully relax and sleep draws very near, let us see what general relativity reveals about the universe as a whole, its origin, evolution, structure, and ultimate fate. Einstein's equations don't just describe gravity locally, they determine the large-scale geometry and dynamics of space-time itself, painting a picture of cosmic history from the Big Bang through the present into the deep future. Apply general relativity to the entire universe and something remarkable emerges. Space-time itself must be either expanding or contracting. It cannot remain static. Einstein initially found this troubling. He expected the universe to be eternal and unchanging. So he added a cosmological constant to his equations to allow static solutions. But observations soon revealed that galaxies are moving apart. Space itself is expanding, and the universe has not always existed in its current state. Imagine, as you rest, running the expansion backward in time. If galaxies are currently moving apart, they must have been closer together in the past. Continue backward, and you reach a moment approximately 13.8 billion years ago when all matter and energy occupied an infinitesimally small region, not just packed densely, but with space-time itself compressed to a point. This is the Big Bang, not an explosion in space, but the expansion of space itself from an initial singularity. The Big Bang was not an event that occurred at some location in pre-existing space. There was no before the Big Bang because time itself began with the Big Bang. Space and time emerged together from the initial singularity. Asking what came before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because before requires time, and time didn't exist before the Big Bang. Picture the universe's history as you drift towards sleep. In the first fraction of a second, space-time and all energy existed in unimaginably hot, dense conditions. As space expanded and cooled, forces separated, first gravity, then the strong nuclear force, then electromagnetism and the weak force. Matter and antimatter annihilated, leaving a slight excess of matter that forms everything we see today. Protons and neutrons formed from quarks. Nuclei formed from protons and neutrons. For 380,000 years, the universe was opaque, a hot plasma of electrons and nuclei with light constantly scattering. Then the universe cooled enough for electrons to bind to nuclei, forming neutral atoms. Light could suddenly travel freely, and the universe became transparent. The light released at that moment, the cosmic microwave background, still fills the universe, now redshifted by expansion into microwave frequencies, observed by satellites as a faint glow in every direction. Gravity pulled matter into clumps. The first stars formed about 100 million years after the Big Bang, fusing hydrogen into helium, releasing light, beginning the process of building heavier elements. Stars clustered into galaxies. Galaxies clustered into groups and clusters. The large-scale structure of the universe emerged, a cosmic web of filaments and voids, matter concentrated along strands with vast, empty regions between. All of this follows from general relativity's equations describing how matter curves spacetime and how curved spacetime evolves. The universe's geometry is determined by its matter and energy content. If there's enough matter, spacetime curves back on itself, creating a closed universe that will eventually stop expanding and recollapse. If there's too little, spacetime curves negatively, creating an open universe that expands forever. If the density is precisely critical, spacetime is flat. Euclidean geometry holds at cosmic scales. Observations suggest our universe is remarkably close to flat, with density almost exactly at the critical value. But there's a mystery. Most matter is dark matter that doesn't emit light, but reveals itself through gravitational effects. And most energy is dark energy, a mysterious component causing the universe's expansion to accelerate. About 68% of the universe's energy is dark energy, 27% is dark matter, and only 5% is ordinary matter like atoms. We live in a universe mostly composed of things we don't understand. As sleep approaches, consider black holes again in cosmological context. When massive stars exhaust their nuclear fuel, they collapse. If the star is massive enough, no force can stop the collapse. The star compresses into a singularity surrounded by an event horizon, a black hole. General relativity predicts these objects must form when enough mass concentrates in small enough volumes, and observations confirm their existence throughout the universe. Supermassive black holes lurk at the centers of most galaxies, including ours. Millions or billions of times the Sun's mass, formed through processes still debated by astronomers. They power quasars, the brightest sustained phenomena in the universe, by converting infalling matter's gravitational potential energy into radiation. They shape galactic evolution, influencing star formation through their powerful effects on surrounding gas. Stellar mass black holes form from individual stars. When two such black holes orbit each other, they emit gravitational waves, gradually losing energy, spiraling closer, finally merging in a violent event that shakes space-time across the universe. These mergers create the gravitational waves LIGO detects, allowing us to observe black holes directly for the first time, confirming they behave exactly as general relativity predicts. The universe's ultimate fate depends on dark energy's nature. If dark energy remains constant, a true cosmological constant, the universe will expand forever, accelerating. Galaxies beyond our local group will eventually recede beyond the cosmic horizon, their light redshifted to infinite wavelengths, disappearing from view. Stars will exhaust their fuel. Black holes will evaporate through Hawking radiation over unimaginable timescales. The universe will approach a state of maximum entropy, the heat of death. Everything at uniform temperature, no gradients left to power any processes. Alternatively, if dark energy changes with time, the future becomes less certain. If it increases, a big rip might occur, expansion accelerating so violently that it eventually tears apart galaxies, then stars, then planets, then atoms themselves. If it decreases or reverses, expansion might halt and reverse, leading to a big crunch. The universe recontracting to a final singularity. Picture yourself as unconsciousness approaches, as part of this vast cosmic story. The atoms in your body were forged in stellar cores, scattered by supernovas, condensed into planets orbiting later generation stars. You are made of star stuff, carrying within you elements created in dying stars' final moments. You exist 13.8 billion years into cosmic history, on a planet orbiting a middle-aged star in an ordinary galaxy, living during the brief cosmic epoch when stars shine and planets exist and life is possible. General relativity reveals that this entire cosmic story, from Big Bang through star formation through your existence, follows from space-time's geometry and dynamics. The universe's evolution is written in Einstein's field equations. The expansion of space, the formation of structure, the existence of black holes, the ultimate fate billions of years hence, all consequences of matter curving spacetime and curved spacetime evolving according to mathematical laws. We observe the universe through relativity's lens and see confirmation everywhere. Gravitational lensing bends light from distant galaxies around massive galaxy clusters, creating arcs and multiple images exactly as predicted. Time dilation affects light from distant supernovas, making them appear to evolve more slowly than nearby ones. Gravitational waves from merging black holes match theoretical predictions with extraordinary precision. The cosmic microwave backgrounds pattern reflects spacetime's geometry and composition in its earliest observable moments. As you drift into sleep, rest knowing that relativity is not merely abstract theory, but tested reality. The GPS guiding travelers accounts for curved spacetime. Particle accelerators couldn't function without relativistic corrections. Astronomers calculate planetary orbits using general relativity for precision. The universe's history and fate are written in equations that have been tested and confirmed across scales from laboratory experiments to cosmic distances, from microseconds after the Big Bang to billions of years in the future. You inhabit a relativistic universe described by elegant mathematics, where spacetime curves and flexes, where time dilates and simultaneity is relative, where gravity is geometry, where black holes exist, where the cosmos began in a singularity and expands still, where your existence is part of a vast cosmic story stretching from the Big Bang through the present into an unimaginably distant future. This is not science fiction, but science fact. The confirmed structure of reality revealed by Einstein's profound insights into space, time, and gravity.